This screencast is going to go over our nuclear chemistry practice problems. So number one was all about how to write these decay equations. The hardest part is knowing the particle that we're dealing with. So in the first one is just the alpha particle, or undergoing alpha decay. So we have a sample of polonium 210 84. And this unstable nucleus is going to give off an alpha particle. Alpha particles are represented by a helium atom because it's 2 protons and 2 neutrons. And then what polonium is going to transmute into is we look at that bottom number first. So what plus 2 gives you 84, and that is going to be 82. And 82 on the periodic table is Pb, which is lead, and then we deal with the top number to figure out which isotope of lead it is. So what plus 4 gives you 210, and that would be 206. There we go. The next one is carbon-14, that radioactive isotope of carbon there. And then it's going to undergo a beta decay. So beta looks like this. It is negative and 0 at the top. It's not going to cause a change in mass. So then what minus 1 gives us 6, and that's going to be 7. And on the periodic table, that is nitrogen. And then there is no change in mass, so 14 plus 0 is 14. We've got some potassium here, and it's going to undergo positron emission. So it looks just like a beta, except it's positive. And then what plus 1 gives you 19, and that is going to be 18. And so we are dealing with some argon there. And no change in mass again, so it is a 38 on top. And here we have some silver, and we're going to see what happens if it goes through electron capture. So this is the only one that's written as a reactant, so it's not a decomposition reaction. So that that electron is pulled into the nucleus. So 47 minus 1 is 46, and we are dealing with some palladium there. And then no change in mass, so it's still 106. All right. Then we have number 2, which is a half-life problem. Our 2, 3, and 4 were all half-life problems. So we look at the first one, and it's a pretty straightforward type of problem. Our first objective is to figure out how many half-lives have gone by, and I see they give me 2 times, a total time and the half-life time. So I'm going to take the total time, which is 415.2 days, and I'm going to divide that by the half-life time. This is just like the example we did in class yesterday. And that's going to tell me that 3 half-lives fit into this total amount of time. Alright, so we start with a 2-gram sample, and that is going to be cut in half 3 times. So after the first half-life, we would just have 1 gram of that sample remaining. The rest of it would have transmutated into another substance. Then after the second half-life, we would have 0.5 grams. And then after that third half-life, we would have 0.25 grams of that polonium remaining. Alright, then we have number 3. And number 3 is another problem dealing with polonium. This time we're dealing with polonium-218. So again, another isotope of polonium. This one has more neutrons than that one, but they have the same number of protons. So the half-life of polonium-218 is 3 minutes. If we start with 16 milligrams, how long will it be till we have 1 milligram? So we're looking for the total amount of time. First, we have to figure out how many half-lives have gone by, and since we don't have 2 times, we're going to have to deal with the 2 amounts that were given. So you start with 16 milligrams, and we're going to cut that in half until we get to 1 milligram. So after the first half-life, we would have 8 milligrams. After the second half-life, we would have 4 milligrams. After the third half-life, we would have 2 milligrams. And it's going to take 4 half-lives to reach that 1 milligram that we're looking for. So 4 half-lives have gone by. Each half-life is 3 minutes. So 3 minutes times 4, because it happened 4 times, is going to be 12 minutes. And that's the total amount of time for that problem. Then, with number 4, we have yet another isotope of polonium. And in this case, we have less protons than we had in number 2, but number 3, but more than we had in number 2. All right, in this particular one, again, this time they want to know what the half-life is. They give us the total amount of time, they give us a starting amount, and they give us an end amount. So we're going to use the starting and end amounts to figure out how many half-lives have gone by. So we have 1,000 milligrams. After the first half-life, I would have 500 milligrams. After the second half-life, I would have 250 milligrams. After the third, I would have 125 milligrams. After the fourth, we're just going to cut this in half again, and that's going to be 62.5 milligrams. And after the fifth half-life, we would end up with that 31.25 milligrams. So it takes 5 half-lives to go from 1,000 milligrams to 31.25, or for it to decay to that amount. And 5 half-lives had to fit in that 820 second total time frame. So 5 half-lives have to fit in there. And if I divide my 820 seconds by 5, I get 164 seconds. That's how long each half-life is.